In this video, I'd like to provide explanations to the solutions of the practice quiz that was included in your blank notes this week. Now, if you've been practicing with the Math Excel assignments and the notes with the videos, I think you can handle most all of these questions. However, these first three are going to seem a little bit unusual at first. I think you can handle them, however. Let me just share with you a technique to make that happen. In this first row, in these examples here, one thing you've got to keep in mind is that if it's possible to rewrite the base of these exponents as a common base or as the same base, then there are some easier techniques in finding the unknown variable without using a logarithm. For example, I know that 125 can actually be rewritten as the number 5 cubed. So if I rewrite 125 as the number 5 cubed, and I now envision that it's 5 cubed being raised to the 2x power, then my law of exponents, or my properties of exponents, would tell me that anytime that I have the base of one number raised to a power and then to another power, the power to a power rule says that I can multiply these exponents to combine them. I have 5 to the 6x power without the parentheses. And if the bases match, if the bases are equal to one another, then the exponents match, or the exponents are equal to one another. So once we see that the base in this case is 5 on both sides of the equation, then we can simply say that x squared plus 8 is equal to 6x. And to solve for x, since this is a quadratic, I should move the negative 6x to the left-hand side. And I can solve by factoring or the quadratic formula. Factoring here is pretty straightforward. I like the numbers 4 and 2, specifically negative 4 and negative 2. So therefore our solutions are positive 2 and positive 4. In a perhaps easier example, we have over here 2 to the negative x power is equal to 32. Well, I like to look at the larger base first and see if I can reduce it, and certainly in this case I can. 32 is the same as 2 to the 5th power. So when the bases match, the exponents match, we now know that negative x is equal to 5. So therefore x by itself without the negative sign must be negative 5. In example 3, we've got e to the 4th power raised to the power of x multiplied by e to the x squared power, and all of that equals e to the 12th. Well, again, with our power to a power rule, e to the 4th raised to the xth power is the same as e to the 4x power. With common bases that are being multiplied, we can then add their exponents. So we now have e to the x squared plus 4x power, and all of that equals e to the 12th power. When the bases match across the equal sign, then so do their exponents. We know that x squared plus 4x is equal to 12. When we subtract both sides by 12, we have a quadratic that can be solved. I think factoring will work here again. I think 6 and 2 will work this time. However, we need a positive 6 and a negative 2 in order to FOIL to multiply to make negative 12, but add or subtract to equal positive 4. And so this tells me that my solution is the set of numbers negative 6 and positive 2. So that technique wasn't something that we talked about in the videos prior, but it is good to recognize in case we can solve equations that way. It is worth noting, however, that it doesn't always work. We can't always get a common base in our exponential problems, and for that reason we would rely on logarithms. So let's see if we can answer these logarithms without a calculator. Remember, the trick here is to set the logarithm equal to x and then solve for x. If you don't know what the logarithm result is by simply looking at it, then consider rewriting your logarithm as an exponential. And now we've got 5 to the x power equals 125. and we know that 125 is the same as 5 cubed, so therefore x must be 3, and the logarithm base 5 of 125 must be equal to 3. For part B, 2 to the power of x is equal to 1/4. Well, 1/4 is the same as 1 over 2 squared, and 1 over 2 squared is the same as 2 to the negative second power, so therefore x must be -2. Once we get the bases to match, we know that the exponents are equal. For part C, 9 to some power equals 3. Well, in this case, it's the 9 that has to be reduced, and I'll call this 3 squared to the x power equals 3 to the first power. We'll call this 3 to the 2 times x, because the power to a power rule does require us to multiply those exponents together. Now that the bases match, we know that the exponents match, and 2x is equal to 1, therefore x is equal to 1/2. And hopefully that answer makes sense, because 9 to what power is equal to 3? Well, 9 to the 1/2 power equals 3, because remember, the 1/2 power is the same as a square root. So 9 to the 1/2 power means the same thing as the square root of 9, and of course the square root of 9 is indeed 3. We would like to expand this logarithm next. We have a single logarithm, and we'd like to split it up into several smaller logarithms. So the first thing that I'm going to do is I'm going to notice that this fraction bar extends pretty widely here. So that basically creates a numerator and a denominator that are grouped as shown here. So the first thing I'm going to use is the quotient rule, and I'm going to take that numerator, place that inside of the logarithm of the same base, and subtract another logarithm with the same base evaluated at the denominator. Working from left to right, I noticed that the natural log of x times y can be split into 2 logarithms. This is our product rule. It says that if there's a product inside our argument, we can separate this logarithm into the sum of 2 logarithms. And then simultaneously here, since this is a separate expression within the problem, I can use the power rule and rewrite this as 4 times the logarithm of z. And now what we're left with are terms based on the natural log of x, y, and z, as was indicated by the instructions here. And so I feel that this is a pretty good answer. We've expanded a single logarithm into, in this case, 3 separate logarithms. For this example, you might notice that the 2 logarithms across from the equal sign have the same base, and that's a good start for us. You might be tempted to say that x must be 9 because of that, but let's keep in mind we've got this extra 2 that's multiplying by the logarithm. So the proper way to solve this is to bring this 2 back inside the logarithm. We're going to condense it. We're going to say that log base 5 of x squared is equal to log base 5 of 9. And now, with the logarithms whose bases match are equivalent, we can say that x squared is equal to 9, and therefore, after taking the square root, we would say that x is equal to either 3 or -3. Let's keep in mind, however, that this x variable, the argument within the logarithm, by definition must be positive. So we'll throw out this -3 as an extraneous solution, and we'll simply say that x must be equal to 3. In this example here, I don't really know what x should be, so that log base 2 of this expression ends up being equal to 6. However, if I consider my loop rule and rewrite this as an exponential, I might be able to get somewhere. 2 to the 6th power is equal to 4 times x plus 5. Now 2 to the 6th power seems like it's going to be a lot, but since it's only the number 2 as the base, I think we can still do this without a calculator. 2 times itself 6 times in a row is 64. And if 64 is equal to 4x plus 5, we can subtract 5 from both sides, divide by 4, and we see that x is equal to 59/4. The nice thing is we've completed this problem without a calculator, so I don't expect to see any decimals as a result. We can simply leave our result as this improper fraction. Similarly, over here, I could use a calculator and evaluate what log base 7 of 343 is. But if I don't have a calculator available, or in this case I'm telling you not to use one, well, we might want to think about this thing off to the side here. And I bet we could do this without a calculator. If log base 7 of 343 is equal to some unknown number, then that means that 7 to some power is equal to 343. And since this is showing up on a no calculator question, or on a no calculator portion of the quiz, then I would argue that you can solve this with whole numbers. In fact, 7 times 7 is 49, so 7 squared is 49. If I multiplied 49 times 7, well, that's kind of interesting. 7 times 9 is 63. 7 times 4 is 28 plus 6, which is 34. And there's that 343. So as it turns out, it was 7 cubed that equaled 343. Therefore, x is equal to 3. So all of that side work was done just to replace logarithm base 7 of 343 with the number 3. And now that we know that 3 is equal to 2x plus 7, we could subtract our 7, divide by 2, and we'll see that x is equal to -2. This time it's perfectly fine for the x value to be -2 because x is not located inside the logarithm where having a negative number would have been a problem. This is perfectly fine. So here again, this whole front page, this first page of the quiz should have been done without a calculator. Let's see what happens if we do use a calculator, what that's going to look like. Well, what I would do is I would try to get this exponential expression by itself. So I'll multiply both sides by 4 and then subtract 1. And that's going to leave me with e to the 2x power equals 11. Now, by definition, I can rewrite this exponential and say that log base e of 11 is equal to 2x. By the way, a logarithm with a base of e should be written as natural logarithm. And again, I'm doing this because of that loop rule. Some base to this power must equal 11.